Hi Math 204 students. These are the class activities for section 3.4 that I am about to work through with you. Okay, we want to find the eigenvalues for this system and classify the fixed point at the origin. Okay, so to find eigenvalues, we calculate the determinant of A minus lambda I. So that matrix is A, and lambda we don't know yet, that's what we're trying to find. So lambda I is lambda times the identity matrix. So this is going to be 0 minus lambda, which is negative lambda. The 1 doesn't change and the negative 2 doesn't change, and then 0 minus lambda is negative lambda. And the determinant of a 2 by 2 matrix is AD minus BC. So this times this minus this times this. So we're going to have negative lambda times negative lambda minus 1 times negative 2. And we want to set this equal to 0 and solve for lambda. So negative lambda times negative lambda, that's positive lambda squared, plus 2 equals 0. So lambda squared equals negative 2, which means lambda is plus or minus the square root of 2i. The square root of negative 2 or the square root of 2i. So we have complex eigenvalues with a real part of 0. So if you go back to the lesson and look at the summary, which is what I'm doing right now. So the summary in the lesson said that if A, the real part, is 0, then the solutions are periodic, and we call it a center. So the phase portrait is going to look like circles centered around an equilibrium point. Okay, so to find the general solution to the system, first we pick one positive eigenvalue. So we have two eigenvalues. You pick the positive one because easier. You only need one, so you pick the positive one. And we're going to compute an associated eigenvector, and we're going to let I be the x coordinate of the vector. And this little negative sign is a typo, just ignore that. Okay, so to calculate an eigenvector, we do AV equals lambda V, and I'm going to use root 2i as my lambda. So A is 0, 1, negative 2, 0, times the unknown vector xy is equal to lambda, which is root 2i times xy. Okay, so this says 0x plus 1y equals root 2i times x. And negative 2x plus 0y is root 2i times y. So they should either give me the same information or one of them gives me no information. So it looks like they'll give me the same information. And I'm going to make my x value I, so and get a y value. So let's just take this like second equation here. If you make the x value I, you get negative 2i equals root 2i y. And this is nice because there's an I on both sides of the equation, so you can divide that out. And you get y equals negative 2 over root 2. Same thing as negative 2 root 2 over 2 or negative root 2. I just rationalized the denominator by multiplying the top and bottom of this fraction by root 2, just to make things look a little simpler. Okay, so we have eigenvalues. We have one eigenvector. we're going to write out one complex solution that looks like e to the lambda tv. So y complex is e to the lambda, which is root 2i t, times v, which is I negative root 2. So there's my complex solution. Okay, I'll go to the next page. All right, we want to manipulate that solution we just wrote using Euler's formula until we have something of the form y real times I y imaginary. Okay, so e to the root 2 it. Euler's formula, I'll remind you, says that e to the I theta is cosine theta plus I sine theta, which means if I want to do e to the root 2t with an I in front, root 2t is like my theta. So this becomes cosine root 2t plus I sine root 2t. And then I'm going to put that into the complex equation I just wrote down that said y complex is e to the root 2t, and I'm going to put the I in front there, times I negative root 2. So this is the same thing as cosine root 2t plus I sine root 2t, all of that, times the vector I negative root 2. Okay, I'm going to write this all as one big vector. So I need to multiply both terms here by I. So I'm going to have I cosine root 2t plus I squared sine root 2t. And then I have to multiply both of these terms in the second entry by negative root 2. So I'm going to have negative root 2 cosine root 2t minus root 2I sine root 2t. I squared is the same thing as negative 1, so let's change that. So I'm going to have I cosine root 2t minus sine root 2t. And then on the bottom, I've got negative root 2 cosine root 2t minus root 2I sine root 2t. All right, now I'm just going to change the order of the addition in the first entry. Here, I'm going to put this term first and this term second so that it has real and then imaginary. Real part, then imaginary part. So I'm going to have negative sine root 2t plus I cosine root 2t. And then the second entry, I don't have to change the order. It's already real and then imaginary. Negative root 2 cosine root 2t minus root 2I sine root 2t. Okay, lastly, I'm going to break this down into a real part and an imaginary part, a real vector and an imaginary vector. So my real entries are negative sine root 2t and negative root 2 cosine root 2t plus I times, so I'm pulling the I out for the second term, and I'm just going to have cosine root 2t and negative root 2 sine root 2t. So we have now made it look like that. Y real and y imaginary. All right, so the general solution to the system is k1 y real plus k2 y imaginary. So y general is k1 y real, which is negative sine root 2t, negative root 2 cosine root 2t, plus k2 y imaginary, which is this parentheses, not the I. We are leaving the I out. That's the whole idea. Is so that we can write down a real solution with no i's in it. So cosine root 2t, negative root 2 sine root 2t. Okay, next problem. We have a system and an initial condition this time. And we are going to find the eigenvalues to start. So I'm going to do the determinant of a minus lambda I. So that's going to be negative lambda, 2, negative 3, 2 minus lambda. That's negative lambda times 2 minus lambda minus 2 times negative 3, which is lambda squared minus 2 lambda plus 6. We'll set that equal to 0 and solve for lambda. I don't think that factors, so I'm going to use the quadratic formula. Lambda would be 2 plus or minus the square root of 4, that's the negative 2 squared, b squared minus 4 times a, which is 1, times c, which is 6, all over 2a, so 2. So this is 2 plus or minus the square root of 4 minus 24, which is negative 20 over 2. So this is a complex eigenvalue. We've got a negative under the square root, so we have 2 plus or minus. I could simplify that radical. 20 is the same thing as 4 times 5. So I can pull the 4 out of the radical and the negative out of the radical, and I'm going to have 2 root 5 I all over 2, which is the same thing as 1 plus or minus root 5 I when you simplify. So there are my eigenvalues. They are complex. The real part is positive, which means that this is a spiral source. Because the 1, the real part of the complex eigenvalue, is positive. Okay, to determine the direction of the oscillation in the phase plane, we're just going to find a vector in the vector field at like one spot, and it will tell us the direction of the swirling. And if one spot isn't enough for you, then do 2 or 3 or 4, and you'll get a really good idea of the direction of the swirl. I think I'm going to do 2, 2. So I'm going to calculate y prime by doing 0, negative 3, 2, 2 times the point 2, 2. So at the point 2, 2, I'm trying to calculate a vector. So 0 times 2 plus 2 times 2 is 4, and negative 3 times 2 is negative 6, plus 4 is negative 2. So I'm going to draw a vector here in the 4, negative 2 direction, which would be right and down, something like that. So I know that this is a spiral source, which means it's going to start at the origin and it's going to spiral out. And I know that by the time I hit 2, 2, it's going to be heading in this direction. So it must be going like this. The natural period and the natural frequency of the oscillation. So the period is 2 pi divided by b, and b is the coefficient is the root 5. So the period is 2 pi over root 5. And then the frequency is just the reciprocal of period, so it's root 5 over 2 pi. In the phase portrait, sketch the particular solution that satisfies the given initial condition of 1, 1. Time 0, we're at 1, 1. So I'm going to plot the point 1, 1, and then I'm just going to draw a spiral that goes through that. So it's got to look something like this. Spiraling out. Suppose that the 2 by 2 matrix B has lambda equals negative 2 plus 5i as an eigenvalue with eigenvector 1, 4 minus 3i. Compute the general solution to y prime equals by. Okay, so I can write a complex solution. Y complex is going to be of the form e to the lambda t v. They've given us a lambda and a v. So this is e to the negative 2 plus 5i t times v, which is 1, 4 minus 3i. Now we're going to have to use Euler's formula to simplify this and get a real and an imaginary solution. So e to the negative 2 plus 5i t, I'm going to distribute the t. So this is e to the negative 2t plus I5t. And that's all times 1, 4 minus 3i. Okay, I'm going to do the little trick that we've been doing all semester where when you have an addition in an exponent, you can rewrite that as multiplying two bases. Now I can do Euler's formula on this piece. This is already real, so I don't have to do anything to that. E to the negative 2t times, Euler's formula says that this would be cosine 5t plus I sine 5t. This is all times the vector 1, 4 minus 3i. Okay, we have, I'm going to distribute this e to the negative 2t into here. And then I'm going to write this as one big vector. So I'm going to multiply both entries of this vector by this whole mess. Okay, so the first entry I'm just multiplying by 1, so nothing fancy is going to happen. It's just going to be the same thing. E to the negative 2t cosine 5t plus I e to the negative 2t sine 5t. And then the second entry is going to be pretty messy. I'm going to have to FOIL. So I'm just going to write out the multiplication for this step, and then I'll multiply it in the next step. E to the negative 2t cosine 5t plus I e to the negative 2t sine 5t times 4 minus 3i. And then I'm going to have to FOIL this parenthesis times this parenthesis. Okay, so I'm just going to copy my first entry so I don't lose track of it. All right, second entry I'm foiling. So I'm going to do this term times this term. That's my firsts. So I'm going to have 4 e to the negative 2t cosine 5t. Okay, and then outer, this term times this term. Negative 3i is going to be minus I times 3e to the negative 2t cosine 5t. And then my inner terms, this one and this one. So that's going to be plus I times 4e to the negative 2t sine 5t. And then my lasts, which is going to be this term and this term. So it's minus I times I is I squared, which is really -1, which becomes a plus. So plus 3e to the negative 2t sine 5t. Now I'll do some simplifying in that second entry. Copying the first entry. Okay, second entry, I want to combine real terms and imaginary terms. So my real terms are here and here. I want to write them together at the beginning. So they're not like terms, so I just have to copy them down. 4e to the negative 2t cosine 5t plus 3e to the negative 2t sine 5t. And then my imaginary terms, again, are not like terms. So I just have to write them down too. Plus I, although I might factor out the I think I'll do that. 4e to the negative 2t sine 5t minus 3e to the negative 2t cosine 5t. Okay, I am running out of room, so I'm going to go to a new slide. I've already copied this last line. Oops. I've already copied this last line into the next slide. Okay, so I need to write this as y real plus I y imaginary. Equals, the real part is e to the negative 2t cosine 5t in the first component, and then in the second component, the real part is 4e to the negative 2t cosine 5t plus 3e to the negative 2t sine 5t. And then I have plus I times the imaginary part, which in the first component is e to the negative 2t sine 5t. And in the second component is 4e to the negative 2t sine 5t minus 3e to the negative 2t cosine 5t. Okay, so that means that y general is k1 y real plus k2 y imaginary. And this is y real. This is y imaginary. We drop the I. And we say y general is k1 times this y real parenthesis There we go. That's the general solution.